discussing task 8.1. So for part A, we have to find all possible shortest path from node S, which is the train station, to every hotel in the map in an unweighted graph. We use BFS as is optimal for unweighted graphs and is able to find shortest path from S to all our nodes. So here's our pseudocode. We give the graph and then we get the node S, which is a hotel. So we first initialize for each vertex that distance is infinity because we don't know how far V is from the start yet. And there's currently 0 ways to reach, so we set the count as 0. And yeah, so first our queue would be S, which is our hotel, and then we dequeued from the queue, and for each neighbor of U, which is currently S, if it's the first time reaching U, as you can see, math dot infinity, so if distance is infinity, then we'll change the distance to 1 and add the neighbor to queue. Else, if we found it as another shortest path, then we'll update the count to 2. That means there's more ways to go to the path. So for part B, we need to make a function where it checks the undirected graph is connected. So we also use BFS as to start from any node, and if all nodes are visited, then the graph is connected. So we have a pseudocode right here. We have a visited, which is a list. Then the queue is a random node from V, and then we add the V to visited. So while the queue is not empty, we dequeue from the queue, and for all the neighbors, if not visited, we add it to the visited, and we put it into the queue so it can be further explored. And then so if all nodes are visited, that means the graph is connected. Okay. So for part C, they're asking for the runtime complexity of a depth first search algorithm. To find a neighbor of a node U using depth first search, we must first scan the entire row of A, U, which there is n elements, which takes O(n) time because there's n elements. And since the depth first search visits each node, so n nodes once, that means it is O(n) times O(n), which is why we get O(n) squared. So for part D, we're supposed to draw a graph and solve the single source shortest path problem by running Dijkstra's algorithm on our graph. And here we have the adjacency matrix. And we start from node 1. So from node 1, we can see that we can reach node 2 and node 6, and we have their associated costs. So we put node 2, node 6, and their costs. We add them to the queue. So by least costly to the most costly, and then we take the one at the front of the queue, which is node 2 in our case, and we process that. So for node 2, we can reach 4 nodes, which is node 4, 5, 7, and 8. And we add the previous cost, which is 3, and the actual cost to the next path. And then we again sort it from least costly to the most costly, add them to the queue. We take the one at the front of the queue again, and then we update. So in this case, it's node 8, and we update from node 8, which is reachable to which it can reach node 3. So node 3 equals to our cost of node 8, which is 4, plus 10, which is the cost to node 3. And then the next one in the queue is 4. And from node 4, we can reach node 6 and node 1. We don't do anything to node 1 because we've previously processed it. So node 6 is processed and added to the queue again. So we keep repeating this process, and the nodes that have been processed before, they don't get updated, and we just get the next one from the queue. So the final graph looks something like this. So from each node we find the next shortest path, and then we just keep expanding and which gives us this graph. And for part E, we say that we are asked that if P is the shortest path from some vertex S to some vertex in T graph, if the weight of each edge in the graph is increased by 1, then will P still be the shortest path from S to T? Well, the answer is no, because we can have, let's say from this node 2 to 7, it's one edge. So if it was increased, it would be just increased by 1. But let's say if it's something like from 1 to 6, where there's 3 edges, even though it might be shorter before, but there's 3 edges, instead of increasing by 1, we might increase by 3, which might not guarantee it to be still be the shortest path. Yeah.